So, what am I supposed to do? Oh yeah, what is ham radio and why the students should be involved here? And I'll outline the local club and its recent activities. My name is Brent MacMillan. My call sign is VE3OTL. And Bruce Lenton here, the proudest thing about his name should be his call sign that he forgot to put down, VE3ZB. And what's so cool about that is he is the only person in the world that has that call sign. Okay, the VA means Canada, number 3 means Ontario, and the ZB is the personal part of that call sign for him. My call sign is VE3OTL, and again, first 2 letters are Canada. The number 3 means Ontario, and OTL is the personal part of that call sign for me. The cool part about that is not only do I have that as my call sign, and usually when I'm writing letters to other amateurs, I put my name, Brent MacMillan, VE3OTL. I also have that on the license plate of my vehicle. Amateur radio operators are the only ones, pretty well in the world, that you can get your call sign on your license plate. Most people get personalized license plates for $300. You get it for 15 when you get a call sign. How cool is that, huh? So yeah, that's something that stays with you for your life. You're the only one that has that, okay? And when you die, unless you will it to a family member, they will not reissue it for, I believe it's 100 years. Well, sorry, let me back up. The call sign's good for 100, yes. 100 or 150 years. By that time, they figure you're gone, right? So, they'll reissue it again if they haven't heard from you. So, yeah, that's the call sign. Now, ham radio, you have to help me out here. Back when I got involved in amateur radios in 1985, the internet was kind of not around, or just in its infancy. Al Gore was talking about it, but it really hadn't taken off. So, and shortly after I got into ham radio, a few weeks later, it kind of exploded, and it was the thing to do, and they had chat rooms and whatever else they had, forums. And I don't know, like I say, I'm not really on the internet too much as far as getting into that. So like I don't do Skype, I don't do FaceTime or any of that stuff. So you have to help me out here. Like as far as somebody asked me before at a meeting, why would I want to get into ham radio? Like when I can have Skype, I can talk. These days you can talk to somebody anywhere around the world, on Skype or whatever. But I think it's still like the phone. You got to know who to call. And this is the part I'm going to ask you to help me out on. Like, do they have like forums or chat rooms, or you can go in there and say, I want to talk to a guy in South Africa, or I want to talk to somebody in Australia or Tasmania or something like that. I don't know. Like, I'm just asking. I don't know. But on ham radio, you can do that. And sometimes as you get experience in maneuvering your way around, navigating your way around the radio world, as far as the radio bands and frequencies, you'll know where people are at what time and at what frequency, so that if you want to talk to, say, Japan, or if you want to talk to Australia, I'll tell you right now, if you want to talk to Japan or Australia, you got to stay up till 1 o'clock in the morning, because it's 5 o'clock the next day. They're just getting home from work. So yeah. So it's and that's when you're most likely to talk with them. But some of the things you can do, and again, getting back to the internet, I don't know if you can Skype the International Space Station, but you can talk to the astronauts on the International Space Station if you are lucky enough. And lucky being for working stations like that, it's like fishing. You got to be in the right spot at the right time with the right bait to be able to snag. And the right bait being got to be on the right frequency and know when they're flying by, and hope that they're on the air, because they don't have really a set schedule. You just know when they're going by. Other thing you can do is a couple years ago I talked to a guy flying U.S. military transport. He was going from California to the East Coast somewhere, and he was coming across Lake Michigan. And this is on Bruce was talking about the 2-meter band there that you're going to get really bored about, but this is on the 2-meter band, so it's not that boring. That he's in the plane with his radio, and I don't know if he's using the radio in he probably was using the radio on board the aircraft because he was crossing Lake Michigan just by Chicago, and I was trying to get in. There was quite a group of people trying to talk to him, around the area in Michigan, Wisconsin, and up here in Ontario. So I was waiting for my chance that he could say my call sign, he could hear me and talk to me. So I was watching his signal go up because he was telling me about what he was flying, one of the great big U.S. military transports, and how fast he was going, 300 miles an hour. It took him about 3 or 4 minutes to get across Lake Michigan, and you watch this on your S meter for signal strength on your radio. You watch the signal go up, and then it faded off as he was going beyond the horizon. So that was pretty cool. I don't think you can Skype anybody that's active military flying one of those jets. And same thing again, quite a few years ago. Driving home from work one night, I had one of the North American radio nets I was listening to in my mobile. I'm driving home from work and listening to this network, which is where a bunch of people joined together to just check in. It was the Maritime Mobile Service Net, and this aeronautical mobile checked in. He said who he was, and he said he was 20 miles west of Sault Ste. Marie. And as soon as I heard that, I want to talk to that guy. So I called him and got him to go off frequency from the net because we didn't want to interrupt the net. And it turned out the guy was flying, he was a commercial airline pilot. He was flying for, they're not active anymore, they're not in business anymore, but one of the big carriers. It wasn't Air Canada, but one of the other ones. He's flying up to Calgary. He was going to sit on the ground for a couple hours and then fly back to Toronto with some more passengers. And he explained he's using the radio that's in the aircraft. Not only do they talk on the aircraft bands, which are not very far off from where the ham radio bands is, but those radios will tune down into the ham radio bands. He's ham radio operator. There's no commercial airline pilots here in the room, huh? or on the on YouTube tonight. And what he said was, it's more or less being a glorified bus driver. Get that thing up in the air, it's on autopilot, they look out the window until they get close to the airport, and turn the autopilot off and land the plane. So we got on, he tuned down to the ham radio bands and talked to people. It was cool. A friend of mine, this is back in the 80s, and this is like 80s, like security was a lot different back then. Talked to Air Force One on his way back from Japan. President Reagan wasn't on the plane, so it wasn't Air Force One, but the pilot was a ham radio operator, just bought a handheld in Japan, flying home to the United States, wanted to try it out. So he's in the cockpit of the airplane as it's going along, flying over Sault Ste. Marie, going CQ, anybody on 2 meters?
Oh my God.
I talked to Air Force One. How cool is that? So that's kind of some of the things you can do. You can if you get into what we call DX, where you work countries around the world, you better buy a good map of the world, okay? Because a lot of these countries that you'll start talking to, the ones that are rare, are usually countries that are uninhabited, that somebody will go, like a scientific expedition will go every once in a while to the island just to do whatever they do down there, like do scientific stuff. Mainly they go there to claim their sovereignty. If a country owns an uninhabited island that's quite a ways away from the home country, they have to go there every once in a while to claim that, yeah, we're still interested in having the piece of land, and it's still ours. Usually, most of the time, like it's a rock coming out of the water, and usually it's in a bad spot, like it's hanging around Antarctica and stuff like that. And so they go in there, it's really cold, it's covered in penguin doo-doo, and they live with penguins they shiver with penguins for 2 weeks while some amateur radio operators come along. They set up a radio and antennas, and they start working everybody's brother, because nobody's been down to that island in like 10 years, and it's one of the most sought after countries because it's an island that's claimed by another country, so it's officially in I guess international terms, it's a country itself. So everybody wants to have bragging rights that they worked Penguin Island or whatever the name of the island is. So you get into working those people, and part of that is the chase. You know, you'll stay up day and night if you're a real avid DX hound. You'll stay up night and day trying to work this station and trying to get through the pile-ups, because like there's like hundreds, thousands of people on the air at the same time trying to work that station, and like you'll spend 3 or 4 days trying to work them, and finally you get them, and so you have 10-second contact. You know, B3 OTL, I have you. 5-9, see ya. Okay. On to the next one. Yeah. And that's the way they work, but you know, it's cool. You know, so that's some of the things I got into on it. And as Mike and Bruce were saying, there are so many different facets of ham radio that you can get into. Whether it's like Rolly, who's operating the TV camera here tonight, Rolly gets into the amateur television part of it, where he has a station at home that he rebroadcasts stuff over amateur TV. So if you have a TV set up on the frequencies operating, which is the old channel 2, I believe it is, you can pick up his broadcast. We have Matt, who I'm very proud to say that this club here is on the breaking edge of stuff that we do here around here in Canada. We have Matt and his brother who operate remote controlled aircraft on amateur radio bands. Cool thing about that is, you know, most of the guys in the radio club, you know, operate the remote controlled aircraft on radio. But on amateur radio, you can go on different frequencies, which means you go farther, and you operate higher power, which means you go really far. So just got to make sure the airplane's got GPS, so if it gets lost, it'll come back. You know. So yeah, that's some of the activities you can get involved in. It can be voice, or it can be Morse code. Everybody's saying, like, what do I want to learn Morse code? Exact same thing I said back in 1985 when I got my ticket. Back then, as part of the course, you had to learn Morse code, and they didn't tell me till towards the end of the course that was the only way I was going to be operate when I got on the HF bands. Which I thought, at the time when they told me I was going to have to learn Morse code, I thought, I'm just going to learn enough that as soon as I pass that course, I'm going to take that Morse code key and throw it in the lake. And but that never happened. I learned that I enjoyed using Morse code. Neat thing about it is when you talk to people around the world, okay, everybody speaks English to some degree. It might be, hi, my name is Vlad, you know, your signal's 5-9, I live in Vladivostok, and I'm out of here, goodbye. Or they may speak a lot of English where you can carry on a conversation with them. But the difference between Morse code and speaking to somebody in voice is you have no dialect to get around. There's no like Irish or Scottish brogue, you know. You know, there's no accent to have to deal with. It's just and does, you know, and you in your head you translate it into letters or numbers. So it's a cool way to operate. There's different ways of operating, and when I come back in chapter 10 on propagation, we'll talk about that. And for me, the coolest part about of this hobby was I'm able to set up a little wire antenna in the backyard of my house there, and be able to talk to people around the world. And it's just the thought of my radio signal goes up into the atmosphere, actually goes beyond the atmosphere into the ionosphere, comes back, and may bounce up and down from the Earth up to the ionosphere again and back down, maybe 2 or 3 times before it gets to the end. But it gets there, and I talk to other stations. So that's fun. So that's what ham radio, or a little bit of what ham radio is about. What the local club's involved is, you know, we promote the activity. Of course, we're doing it with these courses too, and also we get involved in community activities. The biggest one right now is the emergency measures display up. They usually have it up at the Walmart in the spring. We're part of the City of Sault Ste. Marie's emergency measures plan, and so if there is a communications outage, we are a service agency for the Red Cross and also for the city police. And it's happened a couple times in the past, not recently, but like I'd say probably the first one was probably about 15, 20 years ago that they lost the telephone office here in Sault Ste. Marie, actually in Algoma. It was off the air there for about, I don't know, 4 or 5 hours. At the same time, power went out. It was about a night like this, you know, 5 o'clock in the afternoon. Everybody's going home from work, and all of a sudden, boom, out goes the lights, everywhere. And they stayed out for quite a while, and the phones were out for a while longer. So when that happens, like, what do you do? Hopefully everybody just sits tight. But if there's an emergency, like you have an event happen at your house, how do you call 911 to get a hold of them? Because there was no phone service back then. There was no, there wasn't much of a cellular service. And I'll save my talk on emergency measures for another day, because I can talk about that for a while. So really, we have a lot of different technologies today that that help us, but they can also be our Achilles heel too. That they are not invincible if there's a disaster. So that's what the club's involved with. We do an event in June called Field Day, where we get out. Last year was at the Point de Chine and set up a radio station out there in the park, and operate for 24 hours. And that's part of emergency preparedness. So that the idea being that if a disaster happened that took all the infrastructure out, and we have it happen all the time down in the States and in South America. Have a hurricane blow through there, it's going to knock everything, flatten everything down, that trees, telephone poles, and hydro lines and all that. So when that happens, the first people that are back on the air are ham radio operators. So all you take is a little wire antenna, a generator, and your radio, bang, you're back on the air. And that has happened so many times that they're the ones getting the information for the municipal authorities out to the people that are going to come and help them. So there you go. The meetings are not every Thursday, the first Thursday every month at the Seniors Drop-In Center. Everyone is welcome to attend. We have a short business meeting, less than an hour, and then we have a program every meeting, and we talk about one facet of the radio, of ham radio. So, and as we go through the course, you'll notice I throw ham radio and amateur radio back and forth. They both know that they both mean the same thing. Nobody really knows how it ever got the word ham, other than we like to talk and, I guess, ham it up. But there's been a few theories on how the word ham came about. But that's the name, ham radio. So yeah, there you go. All right, thanks.
Okay. Is it possible to go with the video? Not possible.
They thought at one time it was not at the moment. Yeah, but three people that were.
Okay.
I think they were involved with the Senate hearings after the Titanic stuff, when they allocated the band plans for radio. Back in when the Titanic sunk, there was no radio, there was no band plan. You could operate anywhere you wanted, and a lot of the information came from amateurs, not while the ship was sinking, but after the aftermath of it. They were giving reports because the radio operators were wireless radio operators. You're sending Morse Code, and they could decode it. So they were listening in on that conversation on what was happening and where the rescue boats were. So any information was coming back and forth. That's how a lot of newspapers got their stories, to the radio operator back on the coast, even before the main boat got back to. So anyways, that was one of the theories. It was the initials, the first letter of the last name of three people that were involved in it.
Okay, it looks like that little video we wanted to show you is not going to be available. We'll have to do it at another time. And I'm just wondering, maybe we should take it's 15 minutes to, maybe we should take an early coffee break, see what we can do with the electronics, and then Brent will be back to do chapter 2. Okay, coffee break. You're welcome to come downstairs and enjoy a cup of coffee. Okay, as we said, we couldn't demonstrate a base station to you because of the amount of metal in this building. So we're showing you a little 5-minute video here of my base station, and I have the logger program up on the computer. The logger program is connected into the radio, so I wonder if we could roll it. Pray. All right, this is Bruce Lenton, your educational director for the Algoma Amateur Radio Club, And at Great Lakes Honda, we can't show you an actual contact on HF radio, so we have videoed this presentation for you so you could see what we're talking about. Now here is my computer, of course, and I have here the logger program, which is Prolog, and this program I'll be able to enter the call sign of the individual I'm contacting, and it will take all the information from the radio and put it into the logger program. So now I'm going to call CQ on the 40 meter band, 7.065 megahertz. Okay, I've made a transmission, and I'm waiting for somebody to come back. There it is. Okay, there's Dave. Just give our calls. Give me signal port 599. Name. Bruce. Location. Sioux, Ontario. I just passed it back to him. VA3ZB from VE3EGC. Fine business. Bruce. Solid. Solid copy. Your RST 599. And you can see he's 20 over here. Name. Here. Dave. QTH. Echo Bay. Echo Bay, Ontario. So how do you copy? Question mark. And he's giving my call VA3ZB from VE3EGC. I said fine business. You're 599 and 20. Thanks. Okay, told him let's go to signal sideband. He said Roger, Roger. So we'll go to sideband now. Yeah, VE3 EGC VA3ZB. A little bit of QRM there, but got a good copy on you as with the code. And yeah, so yeah, you're putting out 20 over S9 here on sideband and on code. So VE3 EGC VA3ZB over.
Yeah, VA3ZB V36. Point up to 67. We're QRMing a couple guys below it here.
Roger, I'll QSY to 67. Stand by. Yeah, very good. Yeah, I've got you. You're about 15 over S9, which is to be expected, of course. And yeah, there was a little QRM in there. And it took us a little while. We got the video camera set up here, so it took us a little while to get going and get all the lights going. But I appreciate the fact that you stood by. And so so that's very good. So VE3 EGC VA3ZB over.
Yeah, VA3ZB V3GC. Fine there, Bruce. And you're still running the camera and everything?
Yeah, camera's still running, over.
Yeah, okay. I'll give you a rundown on the station here, just so that you know the students know what's going on here. The rig here is the TS5.
Okay, we just going to cut it there because this is a little too long. There's one more mode that we wanted to show you, which was PSK31, but we don't want to run out of time for tonight's lesson. So we could show you the PSK31 another time. So with that, we'll pass it back to Brent, who's doing chapter 2.
All right, thanks, Bruce.
You're welcome. You need a hand?
I got hands.
Okay.
All right, going to pass some stuff out here. The first is my slideshow I'm going to present tonight. And if you want a color version of it there, you'll be able to download it off the Oklahoma Amateur Radio Club. Oh, I need one. AAR Club website there. It'll be on there for you. So what I'm hoping to do is we're going to go through the lesson 2, which is the really the first chapter in the book here. It's called Getting Down to Basics. It's basic atomic theory, real basic electron theory, and it talks about conductors and insulators and current and voltage and all that. So and resistance. So probably a lot of you have been through this before. Okay, we're going back to grade 9 high school here, so please bear with me if as we go through it. I'll try and keep it as light and brief as possible. If you have any questions, do stop me and ask. And I just want to tell you, I am not a teacher. Okay, I work for the telephone company, probably as you can see on the name on my shirt here. So yeah, I'm just new at doing this. I don't usually teach this lesson. I usually teach, and like I'll be back for chapter 10, which is propagation, and I'm a little better at that one. I've taught it a couple times. So we're going to talk about, I guess, basic atomic theory, and you know, everything is we're all made up of you know, human body's made up of skin, blood, muscle, tissue, bones, and all that, you know, for example. And that is comprised of chemicals that make up different things to make the bone and muscle. And the chemicals are composed of elements to make them. And this is, I guess, is the basic building block of making chemicals. And these are the elements. And you know, there's oxygen. One that we'll be talking about a lot, Cu, which is copper. Another one is carbon. I'm not sure which one that is. I think it's C.
Number 6.
Number 6? All right. Okay, thank you. And yeah, so there's elements, okay? And the elements, when combined together, make molecules, which are a combination of these atoms. So for water, the scientific thing for water is H2O. Everybody knows that. So that's 2 atoms of hydrogen, 1 atom of oxygen to make water. Okay. So that's what how molecules are explained. We can go to the next slide. So what is an atom? An atom is, and we have an example of a carbon atom here. It's neutrons, protons, and electrons. Here, the neutrons and protons are in the nucleus, and the electrons are out here floating around in different rings here. And there's some sort of mathematical figured out how many electrons per ring, and I can't remember what it is. I think it's exponential. Was it 2, 4, and something, whatever else after that. So. So we have carbon. Carbon is, I'm kind of jumping ahead of myself. Carbon is kind of like an insulator. It's hard for it to lose an electron in the outer ring. But another atom, say like copper, okay, just because of the makeup of the atom itself, it's easy for it to lose an electron or gain electrons, okay, and when that happens, if it loses an electron, okay, it becomes positively charged because there's more protons than there are electrons. And if it gains an electron, it becomes more negatively charged because it has more electrons than protons. Okay, and that's where they get the idea of positive and negative ions. All right, so we can go to the next slide. So when the battery is hooked up to something that lets the electrons flow through it, they flow from negative to positive. So that's the explanation of it. Okay. I'm just going to refer back into the guide here and make sure I'm not jumping ahead or I forgot something here. Okay, if we can go to the next slide. Okay, so here's another picture of electron flow here, okay? And they talk about conventional flow. Okay, electron flow is going from a negative to positive, but here in the book they talk about conventional flow, and I'm going to refer to that because they probably have a better explanation of it here somewhere. Okay, they talk about the conventional flow is the opposite direction to electron movement, and it goes back to the discovery of before the discovery of the electron, and it's important in transistor theory, which you'll get into later. So in this book, they talk about electron current flow. They talk about current flow as being electron current flow is going from negative to positive. Here. All right, on to the next slide. I should just mention too, again, this is the criteria for starting the course. This is nice to know stuff as far as they will not, I'll point out the stuff that they're going to be asking questions on because I passed around the test questions from the question bank. I went through there and found the ones that are related to chapter 2, okay? In that 4 or 5 page document, not every question on there is related to chapter 2, but most of them are. And we'll have a look at them after, and I'll identify the areas that when I reviewed it, it looked like they were concentrating their questions on here. Okay, so current. What is current? Current is an electric current is a flow, or an electric current is a flow of an electric charge. Okay, So you have those atoms that are transferring that electron, okay? And the electron flow is from positive to, from negative to positive. And so it's a flow of electric charge. In electric circuits, this charge is also carried by moving electrons in a wire. Electric current is the rate of charge flow past a given point in an electric circuit, measured in coulombs a second, which is also named amperes, okay? There could be a question about that. The unit of measurement for current flow is amperes, okay? Usually in electronic circuits, it's milliamps or microamps, okay? If you've got amperes flowing in your radio circuit, you've got some pretty heavy duty current flowing around through there. The common symbol for current is the uppercase letter I, and an ammeter is a measuring instrument used to measure the current in a circuit. And most of your testers that you have today are multi-testers. They can check for voltage, they can check for current flow, and they can also check for resistance. So, go on to the next slide. Voltage. So we define voltage as the amount of potential energy between 2 points on a circuit. One point has more charge than another. This difference in charge between the 2 points is called voltage. It is measured in volts. Voltage is represented in equations and schematics by the letter E. Okay, so if we're doing in the next chapter, you do the Ohm's law, the pie chart E, I, and R. Okay, so that's where you'll be using the letters E and I and also R in your mathematical formulas. On to the next slide. I kind of found, thank God for the internet, you can find all this stuff on the internet here. It's just cut and paste here, right? So this is an example of voltage, okay? And here in this example here, they talk about having a tank full of water, okay? You have the tank filled up with water, and the tank is going into a pipe, okay? So what voltage is the amount of pressure that is right here compared to up here, okay? The amount of that water, the water is pushing down to trying to get out through that pipe. Gravity is wanting it to go down, and it wants to get out through the pipe. So that's what voltage is. It's the potential, the amount of pressure of the water to get out of the pipe. Okay. So on to the next slide, we'll have a description of current. Now current flow is, say that you now have 2 tanks, each with a hose coming from the bottom, same as the one before, okay, but now we have 2 tanks. Except in this example here, one's got a wider hose than the other one, okay? And what they're saying here is they both have the exact amount of water in them, okay? But there's more flow of water in this one because the pipe is wider than there is in this one. The pipe is smaller, so it's less water will flow through it. So that explains what current flow is. It's a measurement of the amount of electrons flowing by this point per second, where voltage is the number of electrons that want to get past that point. Okay, the potential difference between there and here, and current is current flow is the amount of electrons that are flowing past it per second. Okay, on to the next slide. Talk about conductors and insulators. In a conductor, electric current can flow freely. In an insulator, it cannot. Metals such as copper typify conductors, while most non-metallic solids are said to be good insulators, having extremely high resistance to the flow of charge through them. And here I have an example of, well, this is an insulator. Actually, this is a conductor, but and this is an insulated conductor because what this is it's a power cord for a radio that you hook up to a DC power supply, whether a car battery or a 12-volt power supply. If you look at the end of the wire, though, you'll see inside that it's a copper wire. Yeah, you can pass it around. It's a copper wire with an insulation, and some sort of plastic that's wrapped around it there. So the copper itself is the conductor. The plastic that's wrapped around it is the insulator. So that's an insulated conductor that we're looking at. So go on to the next slide. Here, it talks about resistance. Okay, the electrical resistance of an electrical conductor is a measure of the difficulty to pass an electric current through that conductor. Okay. So getting back to our, if we go back 2 slides, was it? Where we had the 2 water tanks here. Okay. Okay, we have the one with the wide pipe and the one with the thinner pipe, the smaller diameter pipe. This has a higher resistance than what this one does here because it's restricting the amount of water flow more than the other one. Okay. All right, we'll go back onwards. Okay, yeah, here this one here. This is the schematic symbol for resistance. It's a squiggly line, and there's the symbol for the letter for it is R, capital R, and the omega sign is the symbol for resistance. Yes, measured in ohms. After the guy who discovered that. Okay, on to the next slide. Okay, so resistors. A resistor is a passive 2-terminal electrical component that implements electrical resistance in a circuit, or as a circuit element. Resistors act to reduce current flow and at the same time act to lower voltage levels within circuits. So I got a couple examples here to pass around here. Found these in my junk box. Amazing things you'll find until you start looking. So, oh wow! Yeah, and there's the other resistor here is that's a little higher power resistor there that doesn't, it's a different shape. It's got the. What's that?
You use that for dissipating gaps.
I don't know how to do that. It had alligator clips on it for some reason. But,
one of those at all.
See if you can figure it
so,
out. How many?
Yeah, that's what a resistor is. On to the next slide.
I'm not sure.
Okay.
All right, so I've got a chart here of different types of resistors, and pretty well the ones that I guess we kind of get familiar with. The resistors that pass around there that have those colored bands on it, those are pretty familiar to everybody. Variable resistors, if you have a volume control on anything, okay, it's got a variable resistor in it, okay. And rheostats. I know in my truck I can dim the lights on it there. It's probably a rheostat that's doing that. Like the interior lights there, you can dim them right down. It's probably a rheostat that's doing that. One thing I didn't bring tonight, and actually I couldn't find one, wire wound resistors. Here usually a little bigger resistor, and you're probably a wire wound resistor. You're starting to deal with a little heavier power on it, whether it be higher current or higher voltage there. That you need a little heavier resistor for that. The reason why we don't fix many electronic components these days, surface mount resistors or surface mount devices, whatever they are. Those little things that look like little dots on the circuit board there that some little laser robot plunked on the board there, and they dipped it through a solder bath. When your little bullfang radio acts up in you and starts doing weird things, doesn't want to work anymore, this is the reason why you take it and you throw it in the garbage and you buy another one off of Amazon.com or eBay or something like that.
I actually just soldered 2 wires onto the corner of one of those.
Really?
Yeah. Trying to get around a transistor, putting in my own.
Problem for me is my fingers are too fat, okay? My vision's gone. I'm too old to do that stuff now. So yeah, check it. All right, so that's different types of resistors. As you can see, there's a whole bunch of other ones there too that for different applications. All right, on to the next slide. Okay, you got to know this, okay? Because they will ask questions on this, possibly, okay? And this is part of basic electronics. There, again, we're still in grade 9 or 10 or something like that. Back in the day with these, before they went to surface mount resistors, you had resistors with color codes on them, okay? And sometimes they, I think sometimes they have more bands than this, but generally they had 4 bands. There was 3 bands that would make up the number, and then the multiplier, and then sorry, 5. Then the 5th band down here would be the tolerance of it, how close they were as far as the value of this resistor. Okay, so I think this is the same as the other ones I passed around. It's orange,
Orange, black, and then
silver?
Yeah.
Orange, black, and silver. Okay, so if it's orange, black, and silver, so it's the first band is 3, second one is 3, black is 0, 330, and silver is what? 10%.
10%.
Yeah. So plus or minus 10%. So that means that this little 330 ohm resistor is it could be 363 ohms, or it could be 297 ohms, or give or take. Okay, for the tolerance of it. And it was the size of these that would tell you the power rating on them. Okay, and when I think of it, I'm thinking these are what? Quarter watt? Yeah.
That's 1 or 2.
2 watt?
Maybe 1 watt or 2
1
watts.
watt. Okay, we're just okay. For argument's sake, we're going to say that's a 1 watt resistor. Okay, so that was the power handling capability of it. 1 watt. Okay, so the resistor color code you need to know, and there's a little saying up here. So it's black, brown, red, orange, yellow, green, blue, violet, gray, white. I don't know why they won't put that on the test as far as that little chart there, but they want you to. Seems like everybody wants you to remember this little saying here. Better be ready, or your great big venture goes west. Okay. Somehow, if you remember that, you'll know that the first 2 B's are black and brown, and then red and orange, and so yellow and all that. So, anyways, there you go. There'll be a question on that, maybe. That's in the question bank. So, all right, on to the next slide. Insulators. The most common example of an insulator is on hydroelectric poles. Okay, and back in the day, in the good old day, and actually that almost looks like telegraph wires there. They used to be glass insulators. Okay, they got away from that and they've gone to porcelain. It must be because it has a higher insulation value than what the glass was, or maybe it's more durable or whatever. But most of the, in fact, all the insulators you see now on power poles are going to be porcelain, and even the great big long ones there they got on the high voltage poles. So an electrical insulator is a material whose internal electric charges do not flow freely, and therefore make it nearly impossible to conduct an electric current under the influence of an electric field. So porcelain is one of them. Okay. Another one is, as we've seen on that wire that went around here, it's that kind of plastic they use for insulation. That's the most common one that you'll run into on. It'll be on wires. Mostly all the wires you'll ever come across are insulated wires. Okay. Rubber's another one. Hydro linemen. Anybody who works around power, electricians, will have insulated gloves for working near power. They'll be rubber. Okay. And another insulating material here is good old electrical tape. Okay. And if it's tape of any value, it will have the CSA standard inside of it, which I don't know where I got this one. It must have been the dollar store, or maybe the things were worn off of it, but it will say the CSA rating on it. Electrical tape is good for 600 volts, and it will be marked on the inside of the roll for that. So that's another insulator. Okay. So on to the next slide. Magnetic fields, and usually these are. You think about magnets, okay? With this was a magnet. There's a south and north here, and we've all had fun there. And you stick them on metal things there, and you put the if you put the two norths together, they want to push apart, and same with the two souths. If you put a north to south, they want to stick together. It's so much fun. But what you can't see in a magnet, they have a magnetic field around them. Okay, and a magnetic field, if this was just a soft iron core, if it wasn't like really a permanent magnet, you can make it a magnet by either by pushing an electric current through it. It can get magnetized and create the field and possibly make this field larger. So magnetic fields are areas where an object exhibits a magnetic influence. The fields affect neighboring objects along things called magnetic field lines, which are these little lines, invisible, that are around the magnetic object. A magnetic object can attract or push away another magnetic object. Okay, on to the next slide. Okay, if you pass a wire through that magnetic field, you will induct a current through it. Okay. And in our book here, it talks about how current can be induced through a magnetic field by passing the wire through it, by having the magnet pass by the wire, which is the reverse of what you just did, or passing both around each other. You'll induce the electric current on the wire. Okay, on to the next slide. Talk about direct current and alternating current. Get back to my car there that had the battery in it. Okay, that battery is DC. It's direct current. It runs off at 12 volts. I think everybody knows that. Your car battery is 12 volts. Okay? And what that means is that direct current, it's a unidirectional flow of electric charge. It only goes one way. Okay. Direct current is produced by sources such as batteries, power supplies, thermocouples, solar cells, or dynamos. And in the book, I think they give quite a few examples of sources of direct current. Probably my favorite is friction. Thank God I don't have carpet in my house anymore, but if I did, about this time of year there, I'd be going across the carpet there and I'd go and touch the doorknob, of a door, and you get electric shock. Where'd that come from? Well, that's from you rubbing your feet on the carpet there and getting that shock. So it can also be caused by heat. Will cause a flow of current. Pressure. If you're a child of the 70s and 80s like I was, you probably had a lot of records. That was before I guess 8-track tapes kind of came along, but they really still, it was the record was the thing to have there. Hang out in the house there on the weekend there and play records and get drunk and stupid with your friends. So how did this? Anybody ever think about this? Like in that drunken stupor, how did the sound come from that little plastic thing and get to the speakers? Well, how it did that was the record would spin around. Remember, you had the little arm that came out and dropped it down. There was a little needle on there, and God help you if you ever dragged that across the record, or even worse, across the turntable was spinning around with no record on it. Bad, really bad. It would make a really bad noise. Okay, but what was happening was that little needle was sitting in the groove of the record, and it would move back and forth as the record would spin around, and it was in between two crystals. And because it was moving back and forth, it was causing an electric current to flow that would go to the amplifier in the receiver, and through the magic of block diagrams, it would come out through the speakers as sound for your listening enjoyment. So that was how that worked. It was called the piezoelectric effect. We just talked about magnetism. Another one is photoelectricity. We have a fine example on each end of the city of photoelectricity. There we have solar farms there. So yeah, we've all driven by them, seen them, how they work. And what it is light striking the surface of the solar thing causes the discharged electrons, causing a flow of current. And then chemical action. Best example of that is these little devices we have here that we can't seem to live without these days. Batteries. Batteries are the greatest example of chemical action there. That's two chemicals in there reacting with to produce electricity. Alternating current. Alternating current is an electric current in which the flow of electric charge periodically reverses direction. Whereas direct current, DC, the flow of I can see I gotta fix this and still on. The flow of electric charge is only one direction. Remember, it was negative to positive in direct current. Alternating current, okay, was positive for a period and it goes negative for a period, okay? And we'll see that in the next slide, I hope. Next slide, please. Oh, here we are. Yes. Yes, here we are. This is an example of direct current. If through the magic of electronic box called an oscilloscope, if you looked at, you could look at direct current and alternating current. And direct current is 12 volts, heads in one direction, it's on all the time. So this is 12 volts at this period of time, this period of time, and this period of time. With alternating current, which is what comes out of the electric, that's it. You gotta help me out sometimes. Receptacles. It's alternating current, so it's 120 volts AC in your house and here at the business here. So, and what AC current is, it goes positive for a period of a cycle, and it goes negative for a period of a cycle, comes back to zero, goes positive again, comes back to negative, and it does that so many times. It's 120 volts that we have for the voltage, okay, and the voltage, and again jumping ahead to probably another part of the course, the frequency of it is 60 hertz. I think a lot of people have heard that. 120 volts, 60 hertz. That means 60 cycles of that wave, one wave, 60 cycles of that per second. Okay. So that's the difference between direct current and alternating current. All right, next slide. So we have a very primitive example of an AC generator, okay, and one side of this ring is negative, the other side is positive. So as it's spinning around, this loop is close to the negative side, as well as this one's close to the this is negative, positive side. We're the same north south, so whatever. So it's creating, it's building in voltage. As these reverse and come around to the other side, okay, they will go the opposite direction. So as they get to the middle of the magnet, it'll be a peak of the voltage. As they move away, it'll decrease down to where it gets to zero, and it comes around to the opposite polarity, and it goes in the other direction. Okay. So that's how you get your sine wave for alternating current. Next slide. So batteries. An electric battery is a device consisting of two or more electrochemical cells that convert stored chemical energy into electrical energy. Each cell has a positive terminal, or cathode, and a negative terminal, or anode. So you can see on the batteries, yeah, there's one end. Actually, probably the best example of it is your 9-volt battery. Both posts are on the top. So yeah, one's the cathode and one's the anode. Okay. So there's classifications of batteries. In the book, they talk about primary batteries. Okay. And primary batteries are a single-use battery, whether it be carbon, zinc, lithium. Still make alkaline too, do they not? Are they in there? Mercury oxide or silver, I think that's saying oxide, batteries. Use them, they go dead, dispose of them safely. if you can recycle them. Secondary batteries are storage batteries, okay? The battery in your car is a storage battery because it can be recharged again and again and again. And they can be lead acid, which is like the one in your car, nickel cadmium, nickel metal hydride, or say lithium secondary. If you have an electric watch, pass this one around because it's just about dead. This one came out of my radio. That little operating tip for you, that if you have a radio that has memory in it, like memory channels in it, and the radio starts getting goofy, change the battery and the memory, the memory channel, or the memory battery in it there. That might help it quite a bit, because that helped mine. The display would start, it was doing weird things, going blank, and wouldn't transmit on frequencies that said it was on, and stuff like. Change that battery. And another important tip, make sure you got power to the radio when you change the battery. You lose all the memory channels, you get to reprogram it all again. So yeah, so but anyways, that's what happened with my radio. I spoke previously, I worked for the telephone company. When the power goes out, your telephone continues to keep working. And generally, okay, we had a couple outages before. That was because the processor that makes everything work, like the big computer, decided it didn't want to quit too at the same time the power went out. It's a bad thing. It's like your computer, you have to reset it, restart it. So, but when generally on a power outage, when your power goes out, your telephones keep working. That's because in the telephone office they have batteries there to keep the telephone system up and working. Okay, and telephones work on 48 volts DC, and the batteries that they have sorry, I didn't bring a picture of them. The batteries that they have in the telephone office would stand probably about this high, they're about this wide, and probably about as deep as that table. Each battery is 2 volts, okay, and they hook 24 of them together in series, okay, just like in your flashlight. You know, when you if you have a flashlight, you put a battery in, you put another battery in, okay, that's a 3 volt. If there's only 2 cells you're putting in there, that's a 3 volt flashlight, okay, because you put a 1.5 volt in, another 1.5 volt adds up to 3 volts when you put them in one after the other, because they're in series. Same thing with the telephone batteries, that they take 2 volt batteries, put 24 of them together in series, it makes 48 volts, okay. Those batteries are they're lead acid, but they're more water in them than I think than acid, because they're very temperature sensitive. Okay, they have to be in a heated building. If you have them outside, they'll freeze. But they're 2 volts, and the current capacity of them is from 2,500 to 4,000 amp hours. So if you short those posts out on that, bad, really, really bad. You'll have an explosion when that happens. So they're very careful around those batteries. So the other ones, they talk about a fuel cell. I've heard about it, never seen one. So coming to a car near you. Also, there's physical energy batteries like solar cells and nuclear energy. That's way out of our league. And so that's the type of batteries there are. On to the next slide. As you can see, different examples of batteries. Sure, everybody's got one of these in their cell phone here. That I know I do. And they are probably a lithium-ion battery. That's a storage battery. That's the latest and greatest type of battery. Very high capacity, very long life on them. On to the next slide. This is just for grins here. This is what the battery looks like in your car there. The lead acid battery's all split up there. It's a gray plate, positive plate, and they get separators and stuff like that. So it's all these little plates all joined together there that they don't touch. But they're just far enough away that through the magic of that acid there, they produce electricity. Interesting thing to, again, getting back to those batteries in the telephone office, this case is clear, because we have to be able to see the inside of the batteries. So they're inspected monthly to see if any of these plates work, or if there's any of the insulation in between them. If any of it falls down, the Batteries will last 20 years, but once they see anything like that happening, battery's gone. On to the next slide here. So, talks about types of circuits. Okay, a closed circuit is has a complete path for current to flow. An open circuit doesn't. So, where the lights are on in the room here right now, we can all see it. That's a closed circuit. If someone were to go over and to flick the switch, it would be an open circuit because the lights wouldn't be on. Okay, so that's pretty well how it explains it. Okay. Remember, I was talking about that those batteries in the telephone office. I said short those posts out, bad things are going to happen. That's a short circuit. Okay, it's a low resistance path, usually made unintentionally, that bypasses part of the circuit. And when two bare wires in the circuit touch each other, generally smoke, sometimes fire, just not good. So as a safety measure, they put fuses or circuit breakers to automatically open the circuit. Okay, and what that is, it's a device that when it senses current flow more than what it's rated for, it opens. Of course, with a fuse, it goes, got to change it again, and put another fuse in, and hopefully you fix the problem or change that fuse again. That's why they went to circuit breakers and hydro panels there. That got tired of me putting pennies in behind this.
Illegal.
It's bad. That's bad. Short circuit. Okay, on to the next slide. So here's another description of or diagram of a closed circuit versus an open circuit. As you can see, the light's on because the circuit battery can make its path going from negative to they're going positive and negative, or an open circuit where there's no path on it. Okay, next slide. Schematic diagram. This is just a nice to know kind of thing here right now. That's what they look like. Schematic or schematic diagram is a representation of the elements of a system using abstract graphic symbols rather than realistic pictures. Right from the words of Wikipedia. So what it is, it's an easy way to show how a circuit is laid out as far as the components inside of it. Because in some of these radios, and if you get a big box radio, if you take the cover off it, you just kind of look and say, wow, where does all those wires go? Well, this is where all the wires go. You can go through, it's like a blueprint. You can follow the path of what's hooked up to what and why. And if you have some knowledge of how stuff works, you can be able to troubleshoot where the problem might be in the electronic device. On to the next slide. Okay, I think this is coming to the end here. Comparing DC to AC. And this is a comparison of RMS voltage or current. As we were talking before, if this was direct current here, okay, it would be that blue line. That would be 169.7 volts because it's measured from here up to here. But if you put a voltmeter, an AC voltmeter measuring voltmeter, and they all do that because they're multi-testers now. You just tell it whether it's DC or AC before you plug the probes into the electrical receptacle there. It'll measure 120 volts. Okay. That's because it's measuring RMS. RMS stands for root mean square. Okay. It's leveling out the value for this sine wave because it's 169.7 volts here, but it's 0 here, and it's in varying degrees here and here. So when they want to know what the value is, the RMS value is 120 volts. The peak value is 169. The peak of this is 169 volts. Okay, I think that's it. Is there any more slides? There we go. All right, on to as I said, I didn't cover everything in chapter 2 there. You'll have to read some of it. Concentrate on batteries. When I look through this, they seem to talk a lot about ask questions about batteries, and also they really like that color code chart. So maybe we'll just do a couple questions here. Very first question: which component has a positive and a negative side? Would it be a fuse, a resistor, a battery, or a potentiometer? And again, the component has a positive and negative side. Oh, you know the answer. Okay, so that would be a battery. Okay, next one. A cell that can be repeatedly recharged by supplying with electrical energy is known as, so this is, it can be recharged over and over again, okay? Is it a primary cell, a storage cell, a low leakage cell, or a memory cell? And it would be a storage cell. Okay. One of the things I forgot to mention, which is the next question, which of the following is a source of electromotive force, EMF? That's another word for voltage, okay? A lithium ion battery, a germanium diode, a p-channel FET, or a carbon resistor. Be A, the lithium ion battery. Okay, the next one, an important difference between a conventional flashlight battery and a lead acid battery is that only the lead acid battery, A, can repeatedly recharged, B, has 2 terminals, C, can be completely discharged, and D, contains an electrolyte. Okay? It would be A, repeatedly recharged. An alkaline cell has a nominal voltage of 1.5 volts. When supplying a great deal of current, the voltage may drop to 1.2 volts. This is caused by the cell's voltage capacity, internal resistance, the electrolyte becoming dry, or current capacity. This is a brain teaser here. Okay, so what happens here is that it's normally at 1.5 volts. You put a tremendous amount of draw on it, okay, so you get supplying a great deal of current, and it drops to 1.2 volts. What's happening? And is it the internal resistance, the electrolyte becoming dry, current capacity?
I would say
D, current capacity?
I would think current
I
capacity.
was thinking the internal resistance to be building up in it because it's could be
Similar
dry.
to
So that's
DC and having a 4-gauge run of wire going in excess of over 10 feet and having 10 volts at the end of it.
Sorry, what's that again?
Well, a car stereo, you run too thin of a
Right?
voltage wire. It's 12 volts where it starts out. By the time it makes it to the amplifier due to DC and voltage drop, it'll run to about 10 to 11 volts by the time it makes it out, unless you use thick enough gauge wire.
Yeah.
Which would lead me to D, current capacity, because it's not able to handle the current.
So this is the battery itself that dropped.
If the battery had a higher current capacity, would the voltage drop? On the idea
Yeah,
of voltage.
and why is it doing that?
What's the question?
Okay, so an alkaline cell has it's a battery's got 1.5 volts. You draw a tremendous amount of current out of it, and it drops to 1.2 volts. And what's causing it to do that? And I was thinking,
It's number B.
I think the internal resistance is building up in the battery. So
Current
it's
capacity is in its physical makeup. There's no way to change that. So.
Just like the voltage capacity starts at 1.5, that's its actual maximum capacity.
right,
Regardless of what happens. It's like a spec.
but it drops. It drops.
I know
Yeah.
that this capacity was 1.5, it could never go higher than that.
No, I know.
It can drop, but I think the current's the same. The capacity is,
Same pole as with the car battery.
You got
cranking it.
the battery here, but this resistance is inside the battery,
Yeah.
and you can't change that resistance. And as the battery gets older, that resistance gets higher. Here's your battery, the end of your battery terminal. So this, you can't touch that. It's inside. So you draw a big current, this resistance comes into play, and your battery's not as good as you think it is. It's internal resistance that causes the drop.
Okay. Thank you, Bruce.
You're welcome.
All right. Let me find something else here. Okay, on the bottom of page 3, on the left-hand side, it says, what would the fourth color band on a 47 ohm resistor indicate? A, the value of the resistor in ohms. B, the power rating in watts. C, the resistance material. Or D, the resistance tolerance in percent. Anybody? Sorry, I don't know anybody's name here, so. Sir?
not that old, we'll just say that guy.
That guy.
I'm gonna go for resistance power.
Right on.
You got it.
I think I'd do that too.
Considering each answer is marked on the next to the question too.
Was it?
Oh,
Smart guy. Huh?
I believe
I wasn't looking at that.
Yeah. How'd we do in that first one? That one with the brain teaser then?
it would be.
Was it B?
Yeah.
What, the internal resistance?
Oh, yeah.
Okay. Whoa.
What, you not trusting me?
Wet it through that one. Anyways, so you get the idea here as far as the, now we know that, hey, it won't be like this on the test, okay, the answer's not going to be in bold, okay, beside the question.
We'll take all these sheets.
All right, so actually, if you want to get the question bank, if you go on Google and type in, probably the easiest way to do it is amateur radio test generator. Okay, that'll take you to the Industry Canada website. Actually, that takes you right to where the amateur radio test generator is. You can, and that's where you can take the test itself, or you can look at the question bank. Okay, you can look at sections of the question bank, or like I did, I downloaded the entire question bank and just went through the questions that I thought were applicable for this this lesson tonight and printed those out. When you go through this too, you'll see there's lots of questions there that are way ahead of where we are right now, and that's because it's 120 pages in the question bank, and they were scattered all over the place as far as the questions for lesson 2 and all the other lessons. So some of the questions are not applicable to us at this time, but by doing that, you can actually you can download that amateur radio test generator, and you can start taking. At some point, you can start taking tests, and that test generator is the exact same test that you will get at the end of the course. That's the test generator. You can take it as many times as you want, because what it does and what we do in the course when we go to give the exam, it generates a new test every time. So it's just drawing questions from that question bank of however many questions there are, and away you go. So there you go. Thank you.
Oh yeah, we can give a hand, sure. Thank you very much, Brent. Are there any questions, concerns, anything you want to ask at this point in time? If not, we're going to adjourn. Okay? Good. See you all on Thursday, where we'll be doing Ohm's Law. And if you really think you know Ohm's Law inside out, you don't have to show up. If you know it inside out, I mean, if you're doing it at work, then you